All right, welcome back. So in the last few slides in this lecture, we are going to directly relate properties of the eigenvalues of the representation of the system A to the to a convex optimization problem. So recall we have this framework where we take properties of the system, we relate them to properties of the eigenvalues, and now we're translating those properties of the eigenvalues to convex optimization problems. In the stability in the Schur and Hurwitz parts, we sort of didn't look at the eigenvalue locations explicitly. We sort of like talked about stability properties. And in this part of the lecture, we will show that you can actually take constraints on the eigenvalues themselves and formulate those as convex optimization problems. So, well, we know that we proved that the property of stability is a necessary and sufficient. There's a necessary and sufficient condition in terms of eigenvalues. In this lecture, it's not quite that rigorous, but it allows us to generalize to sort of more interesting properties, I guess, of the solution at some expense of rigor, right? So specifically, if you've taken undergraduate controls, you may have seen some discussion of various system properties. So if particularly if we look at the step response of a second order system, right? So order system. And so here's the system. I'm off the screen. So here's a system. And we give it a step input. So what is a step input, right? So that a step input is an input that looks like this. This is u of t. And at time 0, it's 0. And after time t, it's 1, right? So there's a step input. So it's at 0, and then it's 1. Right, so that's a step input. So this is the response of the system to a step input. This is y of t. So the output of that is y. And, stability isn't the only property we're interested in. We're interested in performance, for example, right? And so what happens when you give a command to this system, right? So you say move over a meter or something like that. Well, it doesn't always behave perfectly, right? It doesn't immediately. So this is your input. This is your desired location, say, for example. If you have a pendulum here and you tell it to move right here, right? Right. This is your command position, right? Well, it moves there. It moves in that direction, hopefully. And then, of course, there's a question of how it moves there, right? So that's there are three sort of metrics that we sometimes apply to quantify how well it moves there, right? And so those three metrics are rise time, settling time, and percent overshoot. So those can be seen on this plot. So this is I should say actually, this is y of t, right? So this is our command, and you can see that it doesn't move there instantly, right? There's a lag between when you tell it to go there and when it actually arrives there. And when it arrives there, it doesn't actually stop. Maybe it overshoots your command by a certain amount. And furthermore, right, it doesn't actually, so it overshoots that command, and then it like takes a while to like actually get to where its final destination is, which may or may not be, by the way, at your command, right? So it may have actually moved over here, but we're not going to. That's steady state error. We're not going to talk about that steady state error. So, but we don't talk about it, right? So in a perfect second order system, we can quantify this response using eigenvalues. So these are performance metrics. And the three performance metrics that we have are rise time. So the rise time is technically this time, how long it takes to get from point 1 of your final destination to point 9 of your final destination, or actually in this case 0.98. So how long it takes to get from here to here. So that's rise time. How quickly it responds, right? And that can be important, right? So if you want to get to like I don't know, if you want your car to accelerate quickly, right, from 0 to 60, right, that's rise time. The second metric, I guess we'll talk about them in actually out of order a little bit, is percent overshoot, right? So if you tell your car you want to get to, say, 60 miles per hour, and it gets to 90 miles per hour before it gets back to 60 miles per hour, if it overshoots that 60 mile per hour limit, well, you can get a ticket, right? That can be bad, right? So we have this this metric for how far beyond your desired command it goes. And it's a percentage, of course, because it depends on what your command is. And that is this percent overshoot, MP, and it's a fraction. Percent overshoot, and it's a fraction. So it's like, I don't know, like 0.1 would be 10% overshoot. Right. So that's the actual metrics here I should mention are TR, TS, and MP. So I have some inequalities here, but we'll talk about that in a second. So these are the actual three metrics. Yeah, percent overshoot, rise time, and then the third one is settling time. So how long it takes before it stops oscillating, basically. Basically, so the rise to, sorry, actually this was 0.9 of your final destination. So settling time is how long it takes to get to 0.98 of your final value, or plus or minus 0.02, plus or minus 0.02 of your final value, and never leave that envelope again. So obviously it gets to 0.02 here and here, but then it leaves it again. It is only when it gets to that that value, or that interval, that error margin, and stays there forever, does that count as settling time, right? So this is a settling time, TS. So obviously, these are all very important numbers, right? So obviously, you would like, say if you're shooting a missile at an airplane, don't do this at home, by the way. You don't want to miss the airplane, so you don't want to hit like an airplane next to it or something like that. So you want low percent overshoot. You want it to be able to follow the airplane fairly quickly, right? So that's rise time. And settling time, you don't want to miss the airplane. So I guess percent overshoot would be hitting other people, others. Rise time is ability to chase. And then the settling time is don't miss. Right, so you can think of it that way if you like. And what's nice is that in a second order system, at least, we're able to relate these performance metrics to eigenvalue locations for A. Right, eigs of A. Right. So how do we do that? Well, not very well, honestly. These are very in anything other than a second order system, these very quickly become more or less useless. But we're still interested in them because practically speaking, in industry, right, these are how we talk about these performance metrics, right? So we're able to say, or we say anyway, or maybe if we're not able to or not, that a system satisfies a rise time constraint if the natural frequency is less, so that's natural frequency, than this number, 1.8 over rise time, the metric. Likewise, we're able to say that, well, okay, so first of all, let's say the eigenvalues of A are, right? So basically, the eigenvalues of A are represented as the real part plus and minus, because eigenvalues always come in pairs, the imaginary component of the eigenvalue, which actually is called omega d, right? So if we look at the complex plane, which is sigma on the x-axis and omega d on the y-axis, we can mark off acceptable regions of the complex plane by our performance metrics. So specifically, by the way, natural frequency then is the magnitude of this this lambda. All right. So basically, the rise time gives us a constraint on n. So the rise time we want to be we want the natural frequency to actually be greater than this. So if we typically want a short rise time, so actually we want the natural frequency to be greater than this amount, but we're sort of quantifying. So anyway, so we want the magnitude of the eigenvalue to be either greater than or less than some particular value. So that gives us the circle. So there's a rise time constraint on the eigenvalues, which looks like a circle corresponding to the natural frequency. Sorry. For settling time, we have a constraint on the real part of the eigenvalue. Specifically, this is the imaginary, the complex plane. We want it to be more negative than a certain value. So the certain value is given here, right? And we want the real part to be to the left of that, right? We want it to be more. So this is negative sigma. We want it to be to the left of that, right? And finally, for percent overshoot, we can give a slightly more complex constraint on the eigenvalues. Specifically, we want the, here I'll just maybe highlight these, 1, 2, 3. We want the real part of the eigenvalue to be less than the negative, there's a constant here, times the magnitude of the imaginary part. So essentially, so if this is the y-axis, and then the x-axis, this is a line constraint on the real component of the eigenvalue. So if we let's see, change my color here. So if we look at this here, we have two lines here, right, corresponding to two constraints, because this is the magnitude here of the imaginary component. So when the imaginary component is positive, we want the for the percent overshoot, we want to be to the left of that. And when it's negative, we also want it to be the left of it. It's just we have to switch the sign there, right? So we always want the sigma to be to the left of this line here, which corresponds to percent overshoot. So I'll change my color again. Right, go for pink. So that's the percent overshoot constraint. The rise time constraint is a circle, and then the settling time constraint, we want to be to the left of that. So basically, our region of the our acceptable region of the complex plane then looks something like this. Right. So we constrain our eigenvalues to be to the left of this line, below these sector constraints here, these two lines. And for the rise time, well, typically actually we want to be to the left of this circle as well. So we want the magnitude to be greater than. So we want to be outside the circle typically. That's a little bit harder to constrain, and we'll talk about why that is later. But basically, so we want our eigenvalues to be in this orange region here, right? I say it's a little bit tricky because this orange region, if we add the omega n constraint, it's non-convex, right? Because you connect those two lines and it's non-convex. So there's a little bit tricky there. We'll talk about that later. So basically, if z is the eigenvalues of A, right, we have constraints on those eigenvalues. So rise time, right? We plug in for our value of omega n, and here we get this omega n, and we get an inequality constraint on the eigenvalues that looks like this. For settling time, right? We just plug in for well, what is sigma? It's the eigenvalue plus its complex conjugate. That gets rid of the imaginary term, and so it's the eigenvalue plus its complex conjugate divided by 2 is less than this term. So another inequality constraint. And for % overshoot, we get this third constraint on again, right? It's z plus z star, where actually we've swapped out our positions here, so that we have a constraint. So we swapped. So this is a sigma, and this is omega d, right? So you see this thing is inverted, right? See. Right. So we have an inequality constraint on z that looks like this. There's a magnitude here, which is going to be a little bit problematic later on. But basically, these are, each of them, convex constraints on the eigenvalues. Or in the case when they're combined, the intersection actually is not convex, as we showed here. Right. But each of those inequalities by itself is a convex constraint. So how do we enforce these constraints on the eigenvalues of a system? Because remember, the eigenvalues of a matrix are this horribly nonlinear, impossible to compute function of the elements of the matrix itself. So how are we going to enforce those types of constraints? Right. So fortunately, we have some very nice results, very powerful results. Two of which two we'll give. The first one is due to Gutmann, right? Again, everyone gets their name on them, which gives us a constraint, a way of translating the constraints on the eigenvalues into constraints on an LMI constraint on the elements of A itself. Right? And notice we have a variable here too. Right? P greater than 0. As I said, right, P again represents a Lyapunov function in some way, but I won't get into the mathematics of how this thing is derived. Right? So this is actually this is very nice because now if you look at this term here, right, what is this term here? Well, this term is basically any polynomial in the eigenvalues and their complex conjugates, right? Basically, almost any polynomial. So this allows us to express almost any polynomial constraint on the eigenvalues of A as an LMI, right? And how does that work? Well, basically, you take the constraint, right? Your constraint on the eigenvalues, and you put a little p in here, right? A p goes in here, and you replace z with A. Of course, z star goes to A transpose, but other than that, it's otherwise unchanged, right? So z goes to A, and z star goes to A transpose. And through some miracle of mathematics, right, this LMI constraint, when you've done the substitution, is equivalent to the constraint on the eigenvalues themselves. So that's pretty cool. So this gives us a relatively powerful and versatile way of expressing constraints on the eigenvalues of A, at least if there's only one inequality constraint, constraints on the eigenvalues of A as an LMI. This is LMI2, and technically this is LMI1, which makes P a candidate Lyapunov function, basically, LMI1. Right. So this is very nice in several ways. So first of all, the constraint set on the eigenvalues does not need to be convex. So not necessarily convex. So a non-convex constraint on the eigenvalues translates to an LMI, convex optimization problems. Right. So that's very nice. Right. This is convex. So any non-convex constraint on the eigenvalues can be translated, basically almost any, to a convex optimization problem. So that's very, very powerful. It does have drawbacks, however. First of all, there can only be one constraint. Right? Only one constraint is allowed. So that's so you have to choose. Rise time, settling time, percent overshoot. You can't get all three. Although if you were to somehow like encapsulate this region, right, sort of represent it using a polynomial inequality somehow, then you could apply Gutmann's method. So maybe can you approximate this as a single constraint? Maybe. Polynomials are pretty powerful. It's you can approximate lots of things with polynomial inequalities, a single one even. Right. The other drawback, however, is that the LMI that you get is not convex in A. Now, this isn't a problem at this point because A is not a variable, but it will be later on when we get to controller synthesis. So there is going to be a problem with controller synthesis using Gutmann in that it's hard to convexify, not always possible. Right. So that's Gutmann's result, which would seem like it would be fairly straightforward. So let's see how it works in practice. Right. Well, I guess actually I don't do it in practice because all of our constraints actually are convex, but before I get to how to implement these things, we're going to turn to a generalization of Gutmann's, or an alternative to Gutmann's representation, which is Chalali's representation. Now, for this, in this case, for this representation, we are going to require that the inequalities on the eigenvalues are going to be convex, right? And in particular, right, we're going to require that the constraints on the eigenvalues have this form here. Right. Specifically, it's called an LMI region of the complex plane. It is of the complex plane. So we're still working in the complex planes. This is the imaginary part, and this is the real part. But basically, can we represent this two-dimensional complex region, some region of the complex plane, like this, right? Where we're looking for this region here. Can we represent that using LMI on the eigenvalues, right? So basically, it's like an LMI where the eigenvalues are the variables. Right. So we haven't really talked about, how to what the feasible region of an LMI looks like, right? So it's not exactly clear what kind of regions this corresponds to. It's very abstract, right? Well, basically, you have to have it has to be linear, right, in the eigenvalues, the constraint that you get, which is going to be a problem with the performance metrics we had because they were nonlinear. And so, so linear in the eigenvalues. There can be multiple ones because remember these can be matrices. So you can have, like, if you had 2, right, you could just use block diagonal matrices, right? So F1 and F02, right? So you could just add these, concatenate these together. Z F21, F22. So multiple constraints is not a problem. It's so the formulation is a single constraint, but if you have multiple constraints, you can just concatenate your use a block diagonal structure to add a bunch of them together, right? So this is equivalent to, right, F01 plus F11Z plus F21Z star less than 0, and, right, F02 plus F12Z plus F22Z star is less than 0. Right. So we can represent lots of regions like this. For example, any intersection of hyperplanes, for example, could be represented like this. But of course, the performance metrics we proposed did not necessarily have that form. Fortunately, however, remember, I mentioned in the previous lecture 3 about the Schur complement as our sort of go-to go-to method for converting what seem to be non-linear inequalities to linear inequalities, right? And so what we'll find is that the Schur complement allows us to do that for the performance metrics that we mentioned. So in particular, let's take a look at the 3 of them, right? So what are they? How do we represent these constraints on the eigenvalues? So there's the one for the rise time, here's the one for the settling time, and here's the one for the percent overshoot. They don't look like LMI constraints, right, because of this term here and because of this squared term here. This one already is an LMI constraint, LMI region, right? Because it's linear in Z and linear in Z star, and there's just a constant term here. Right. But these other 2 need some work, right? Answer is, as always, Schur complement, right? So we'll first do this one, right? Well, let's remember the Schur complement from the previous slide, right? Schur complement gives us a way of formulating things like this, which are quadratic in Y, in terms of things which are linear in Y, right? So these 2 are equivalent. In this case, right? So if we just, right? Just write down the Schur complement again. Right? Here's our Schur complement. We can. This is in this case negative definite, right? If and only if this is positive. So here Z is our Y. This is our, what did I call it? X, I think. And there's no Z. Z is just 1. Right? Right. So if we swap that around, we get this R squared term here. So we're going to call this whole thing R squared. We get R squared minus Z star Z greater than or equal to 0. That's what we want. So apply the Schur complement to that, and that's squared, sorry, not 2. We apply the Schur complement, right? This middle term here is already positive, right? So not an issue there. And so we can just write this out: R squared Z star, and actually we'll divide the whole thing by R, so we get an R there and a over R here. So actually our Z is now actually Z inverse is 1 over R, right? And so we'll just move that other R over there, right? So and then of course we have a negative sign here, right? So then we can represent this using the Schur complement as an inequality on this larger matrix. Right? And so now this has the form of an LMI region. This is our F0. This is our F1, which multiplies Z. This is our F2, which multiplies Z star. So we can use the Schur complement to get something quadratic there's our R inverse, to something which is an LMI region. As I said, this one's already an LMI region. This one's a bit trickier, and I think I have a more detailed explanation on the next slide. But basically, again, applying the Schur complement and noting that Z plus Z star is less than 0. That means the sigma is less than 0, making that assumption. Because that's implied by the constraint itself, assuming Z star is less than 0, this is negative definite if and only if this matrix here is negative definite. And I'll actually go through the derivation a little bit on the next slide. But basically, you can see that this is an LMI constraint, right? There are no constant terms here, right? There's so F0 is 0. We pick off all the terms which multiply Z, there, and there. So we get pi L blah. So 4 terms here. Remember, this is the percent overshoot. And we next pick up the terms which multiply Z star. There's a negative term here, a negative term here. Otherwise, they're the same. So we get pi, negative here, and actually this should be negative as well. I think I'm missing a negative sign there. So how does the Schur complement work in this case? Well, I got a quick it's not quick derivation, but here it is. Basically, we apply the Schur complement to this matrix here, which shows that this matrix is positive, assuming that this is positive. If and only if, right? So apply the Schur complement. This is X, this is Y star, this is Z, right? So that's X minus Y star, there's Z inverse, and so this is Y star, and that's Y. Constants pull out. So that's relatively straightforward. Next, we multiply the whole thing by Z plus Z star. Now we'll multiply the whole thing by negative Z plus Z star. Now Z plus Z star, remember the real part of Z is negative. So negative of the real is positive, so it doesn't flip the sign. That's what we're concerned about. So we multiply the whole thing by negative pi Z plus Z star, and then we get Z plus Z star squared here, and it pops out of the denominator here. Now we multiply the whole thing by negative 1. The sign switches, the inequality switches, right? And then we just move things around. Well, Z minus Z star, conjugate Z minus Z star is just the magnitude of Z minus Z star. Again, this is the imaginary part of Z, right, squared. And so we get a squared here. And so we just move this over to the other side, right? And so this is equivalent to Z minus Z star squared minus this constant term times here. And then we just take the square root of this, right? Because the square is monotonic, that's equivalent to this term right here. And so we just dropped off all the squares. And so this is, of course, the overshoot condition. So we've taken this sort of sector inequality and showed that this sector inequality, remember, it looks like this, right? So we're looking for this region here. So we've shown that the sector inequality can be represented as an LMI in the real and imaginary parts of Z. Right. So we've shown that all three of these performance metrics can be represented as constraints on the eigenvalues of A, and that those constraints on the eigenvalues of A, each individually, can be represented as an LMI region. So we have three constraints now, each represented by an LMI region. But of course, you can concatenate these constraints into a single constraint, right? So we have the F01, F02, F03. So we just make a diagonal matrix with each of those LMI constraints in it, and that becomes our new F0, right? So we make these bigger matrices. So it's a single LMI constraint. Of course, an LMI constraint has to be convex. Unlike the Gutmann condition. But if you're willing to go with that, to run with that, this convex constraint on the eigenvalues of A can now be translated to an LMI on the matrix A. So the eigenvalue, an LMI on the eigenvalues of A can be converted to an LMI on the matrix A itself. Right. So how does that work? Well, okay, it looks like, what is this weird, like, I think this is from, like, what is it, the X-Men, right? It's like the X-Men constraint or something. This is don't be too scared. That's the Kronecker product notation. Okay, what is a Kronecker product notation? Well, okay. What is it? It's not that hard. It's just basically a way of dilating the matrix. So making this LMI bigger, right? So this was an LMI in the eigenvalues of A, and now we're just making this LMI much bigger, n times bigger, where n is the sort of the dimension of A. A is in n by n, right? So this, if F is originally, say, our k times k, right? Our LMI constraint then becomes in nk times nk, right? So it gets much bigger. And how does it get bigger? Well, basically what you do is you take F, right? This is F0 here. And it's a bunch of scalars, right? It's a matrix, it's a bunch of scalars. So these are all scalars, right? And every scalar in F, you multiply it by P, right? So this is a scalar. This is a matrix, right? So the Kronecker product of a matrix times a matrix is just all the scalars in that first matrix. Each of them gets multiplied by the matrix P, right? So it becomes much bigger, right? So, for example, this first term here, right? The constant term, this is the constant, gets Kroneckered with P. P is the variable. Right? Again, it represents a Lyapunov function, but again, I won't get into the mathematics behind this. So this is our first LMI constraint, which is rather small, LMI1. And then it becomes much bigger. It becomes n by n. This is LMI2. So the first term, of course, is linear in P. The second term is the same thing, except instead of multiplying all the scalars by P, multiply them by AP. So, right, F11, F12, F12, F22 times AP is, right, F11 AP, F12AP, F12AP, F22AP, right? So again, linear and AP, right? And again, you multiply these scalars by each of the terms, right? That's just what the Kronecker product does. So the second term, right, is linear in AP, and the third term is linear in AP as well. So that's useful. So this very nice result from Shalali and Gahine says that if I have an LMI constraint on the eigenvalues of A, that can be translated to an LMI in the matrix A itself with this variable P. A is not a variable; it's data in this case. So, for example, right, how do we implement this? Well, here's the rise time constraint. Remember, this is our LMI region. LMI on Z, right? And so what do we do? Well, again, right, this gets Kroneckered with P, this gets Kroneckered with AP, and this gets Kroneckered with AP transpose, right? So there aren't many terms here, right? So there's two terms in here, right? That gets here, there, and there, right? So this gets multiplied by P, this gets multiplied by P. This gets multiplied by AP, and it shows up here, right? This term goes there, this term goes there. Oops, I got it backwards. This term goes there, this term goes there. And this term, there's only one element, and it gets goes down there, right? It gets multiplied by AP transpose, and it pops up there. So we now have an LMI in A for the rise time constraint. Settling time constraint, it's a scalar, right? It makes life a little bit easier, right? So again, the constant term, right, gets just multiplied by P, right? There it is. That's alpha here. The Z, right, is just 1. The coefficient is 1. It just becomes AP. The Z star just becomes AP transpose. So again, an LMI in A. Finally, the percent overshoot constraint we showed. I don't have actually the LMI here, but we can figure out there was no, right, F naught is 0. There's no constant term, so there's no terms in here which don't multiply P. So these are this was Z, this is Z, this is Z, this is Z. So every term in the LMI that had a Z in it, right, the Z becomes AP, right? And every term that had a Z star in it becomes AP transpose, right? So we again get an LMI. Those terms all get added together, right? So we get an LMI in AP here. Or technically, P is just the variable, so it's an LMI in P, right? And A appears, right? So again, what's nice is that we can, concatenate all of these F's together, right? And so we can separate out the LMI constraints and just add them in. So we can have as many as we want or as few as we want. We can just add new LMI constraints as we like. All right, so this is the one for rise time. This is the one for settling time. And this is the one for percent overshoot, right? And so we just add these LMI constraints, and so in YALMIP, right, we add LMI 1, then we'd add LMI 2, and then we'd add LMI 3, and then we'd add LMI 4, and we just add these sequentially just by doing the AP plus P AP transpose plus alpha P less than 0, right? So we just concatenate our constraints with a new LMI at each time, right? And so we get it's relatively straightforward to implement using YALMIP, right? Again, I don't have the implementation of the YALMIP code, but again, this allows us to rapidly construct LMIs, translating performance metrics to constraints on the matrix A itself, introducing the variable p as well. So we've very rapidly expanded our set of LMIs. Again, just basically generalizations allowing us to use these Lyapunov functions, these quadratic Lyapunov functions, to prove properties of the system, or in this case, prove actually properties of the representation of the system, A, right? Because remember, A is the representation. And so we now have not one, not two, but really, I guess you could call it 5 LMIs, 1, 2, 3, and then stability. And we had a sureness of the discrete time system as well. Now, of course, this begs the question of whether one could use these constraints to study discrete time systems. Of course, you could, right? I mean, can we do d-stability for discrete time systems? Well, yes. Remember, sureness, for example, right, is just the circle. The problem is rise time, settling time, and percent overshoot. In continuous time, like the constraints on the eigenvalues of A were pretty dodgy to begin with. And in discrete time, we just don't have an equivalent, right? There's no easy way to translate properties of the transient response of a discrete time system to eigenvalue locations of A, right? Right. If you could use Chilali or Gutmann to represent those constraints. It's just we don't have good constraints on the eigenvalues of A which translate to system properties for discrete time systems. Now, if you want to find such a thing, right, maybe make them up some way, find something, that would make a great course project. I'm not aware of anything that exists in the literature. Or you could, and then you could add it to Wikibooks. We'll talk about the Wikibook project more later. So in any case, summarizing, we've shown that the properties of the system, which is what we really care about, properties of the system, in this case properties of the transient, can be translated in certain cases to, say, eigenvalues of A, right? And eigenvalues of A can certainly be translated to LMIs, right? So we can represent constraints on the eigenvalues of A using LMIs. Now, how many properties of the system we can represent using eigenvalues of A is an open question. And so actually, as we move forward in later lectures, we'll mostly abandon the whole idea of eigenvalues in later lectures. Well, not completely, but mostly. We'll see. You'll see. That concludes our interest in eigenvalues in general. And in the next lectures, we'll talk about controllability, observability, there will be a last gasp for eigenvalues. But at some point after that, we'll have to abandon it because they cease to be useful. All right, so I'm going to stop recording here, and I'll see you all in discussion and in lecture 5.